Good morning. Welcome to the IEPG meeting at IETF 105 in Montreal. Hopefully you're all in Montreal. Okay, there's no note well. Jeff will get angry if I do the note well thing. Yeah, he would. We have five presenters, sorry, and potentially a sixth. So we're going to skip along pretty quickly between the presentations. If you have any questions, I guess the presenters can take those as they see. First up is Joel. We have about 20 minutes per person. Okay. If you don't need that much, that's good. Please, to the presenters, remember, you have to speak into the mic or people can't hear you. And you want to stand on the pink X so that the Medico people see us. And there's a clicker, and I'll get your presentation.
All right. Yes. These graphics are better than mine since I basically don't draw stuff. Yeah. So this is actually sort of still recent news. Some of us have been more exposed to this than others, but basically anyone with a Linux box has done a little bit of work in the last month due to this particular complex of vulnerabilities. So, I mean, the basic gist of what's going on here is that there are various ways to panic your kernel using really small packets. And if you're a malicious client, you can actually get the server to participate in this by setting your TCP MSS rather low. One of the proposed mitigations, assuming that you cannot simply reboot all of your machines in a big hurry, is to limit the minimum size MSS that you can actually set on a connection. So in the CVE, one of the proposed mitigations is actually the IP tables lines that you see here for IPv4 and IPv6. You know, hopefully nobody is actually advertising a TCP MSS of 500 on IPv6. I'm not sure why we would consider that legal, but as it turns out, people actually do. So before I actually went and slammed that mitigation on several thousand Linux machines that serve millions of connections per day per box, I went and actually looked at two questions. What is a legitimate TCP MSS? We can go back to some fairly foundational documents with respect to IPv4 to look for advice there. Obviously, at one point in time, the default maximum datagram size was 576. Really, it still is for v4. You can, of course, obviously send a packet that's smaller than that, down to the size of your minimal amount of data that's associated with your TCP ACK, so about 60 bytes. One of the things that you get in advice on the size of IP datagrams, not on the TCP MSS, is that hosts actually must be able to receive a datagram of 576 bytes. If somebody sends you an MSS of like 48 or 64 or 200, despite that, you should be able to send them a TCP packet that's bigger than that. Otherwise, they are violating RFC 791 as far as I can tell. So that portion of mutual negotiation that's supposed to occur isn't reinforced by strong rules about how things are applied in TCP. RFC 2460 sets the IP MTU for IPv6 to 1280 minimum, right? So that means that the MSS you should be able to send a packet with that someone can receive from that would follow on to be 1240 or so. So before I actually went and whacked 500 on there, I actually went to see on our network what MSSs do we actually see on packets. So I looked in our flow data, and that was kind of entertaining, but I didn't really believe it. So I just captured 100 million SINs from 5 different locations in the network, and then captured all the values that were there. Yeah, so they do actually all fit on one slide, I guess. You will see that the largest one that's there is 65496, and the smallest one is 0. I think both of those are rather optimistic on the part of the sender, right? There are some that are pretty common. I think the most common, very small one was unsurprisingly 536, so 576 minus 40 bytes. There were 3,000 odd packets or SINs with that MSS set on them out of 100 million. So many of these are pretty rare. They're both. I don't really, you can actually see in this one, if you do some quick math, what percentage of the TCP SINs that we see in those pops is actually V6. But this is actually the percentages for the common MSS sizes as sampled from 100 million SINs. You know, fortunately for our expectations, 1460 and 1440 are pretty highly represented in this distribution. 8960, interestingly, it's actually hard for me to separate out the portions of my network infrastructure that use that, because we speak 9K MTUs back and forth to each other, from the portion of the internet that optimistically suggests that it can support a 9K MTU. I would say that for anything bigger than 1500, they're basically counting on path MTU discovery to work. That's interestingly optimistic. But for the most part, we clamp those on their behalf so that it doesn't have to. So these are obviously just the MSSs that they sent us, not what we sent back. Okay, so if we look down here at the bottom, because I wanted to know if I was going to block small MSSs because malicious clients might be using them, what sizes would I see commonly down at the bottom? So out of 100 million samples, the only one that gave me pause was this guy at 512 and the one at 256. Those seem like interesting choices. Interestingly, I didn't see those in all of our pops. Many of these oddball ones appear only regionally. So there are particular providers or clusters of devices that seem to be associated with these kinds of behaviors. They're not generalized, i.e. The 256 one was most commonly seen in Northern Virginia. When I actually specifically filtered that, the rate increased. So I can intuit from that those clients were not very happy when they got filtered. So in fact, when I built a mitigation for this and socked it away for future use, we put the threshold below that 256 number, because even though we are down here in the 10 to the minus 6th or 10 to the minus 8th in terms of frequency of things that we see, there's an awful lot of those. I guess in looking at this, one of the things we have to ask ourselves is what problems were exposed here. There's a generalized problem of poorly understood and infrequently exercised code paths. So we see a number of kinds of vulnerabilities, like that. IP options handling, IPv6 packet too big handling. And some of these are apparent in more than one operating system and in separate implementations. So some of these things are a product of interpretation of IETF standards, much like, say, routing header 0 type vulnerabilities were. There are implementers out there that are looking at the advice that we provide and producing configurations that are notionally feasible but not necessarily compliant, or maybe they're completely illegal. But MSS is lower than 536 or 1240 seem to fit into that category. So when you see those and they're the product of, say, additional encapsulations, where someone has set their MTU lower deliberately because they're doing PPPoE, for example, those are all well understood. So if you see an MTU of an advertised MSS of 1388, it's pretty obvious what's going on there, right? But these 512 and 256 seems like numbers that someone picked out of a hat. Like you didn't arrive at those because of the structure of your link MTU, for example. One of the things that's exposed here is that malicious clients are able to control the behavior of servers, right? When you advertise a lower MSS than the server would prefer to use, the server is going to use that unless it has a knob to prevent that. And now Linux actually has one of those now as a product of this particular vulnerability. But that's a behavior we try and avoid in lots of things, is to avoid cases where the client can specify things that you really don't want to do and you end up doing them anyway. So there's also a need to mitigate certain kinds of behavior, either temporarily or indefinitely, without gratuitously breaking users that have made bad assumptions. That's why I didn't use the 500 value in my own mitigation. So is there some advice we should be offering here? RFC 6691, for example, went back to what we specified for MTUs and how to calculate offsets, and provided better advice, basically because of a lack of clarity. I think there's some argument to be made that there's more clarity that we could provide to implementers that would either prevent this sort of behavior or give me as a user license to ignore these things as bad behaviors. So the Linux kernel now actually imposes a minimum. That minimum is pretty small. It's 48. You can set that higher if you'd like. So if somebody proposes a lower MSS than that, you won't use it. So in our case, like we plan to set that to 200. That's not actually deployed yet, but there you go. So our reading of the document suggested we'd be well within the IP and TCP protocol specifications to enforce sending packets at minimums that are aligned with the minimum link MTUs or some value near them, as opposed to at 0 or 60 or 48. If these devices actually have link MTUs that will not accommodate a 576 or 1280 byte packet, they will break. Obviously in v4, the network could fragment those on your behalf. In v6, it won't. So too bad. Yeah.
Anybody have any questions, comments? Nope.
Thank you.
You're on. Thank you. Next. Yes, sir.
Good morning. I'm Kazunori Fujiwara from JPRS. I will talk about attack to PassMT discovery. It is a part of OARC 30 presentation this May. Attack to PassMT discovery is presented by IP fragmentation attack on DNS at RIPE 67 meeting October 2013 and Domain Validation Plus Plus for MTIM Resident PKI at SIGCOM SIGSAC 2018. These papers show that some implementations accept ICMP fragmentation needed on the DF set with small MT value less than 576 and record specified value as PassMT value. And PassMT value can be decreased to 552 on Linux 3.13 or older. And the paper says that PassMT value may be decreased to 296. Then I would like to evaluate the attack. This page shows evaluation method of the attack. First, generate crafted ICMP packet details in next slide. And second, send the packet to the target. And the attacker is third party. PassMT value is target server and another machine. And number three, verify the result on the target machine using commands. On Linux, IP root get IP address command, and on FreeBSD, syscontrol or net-inet TCP host cache list. On NetBSD, netstat -r shows PassMT. This page shows how to generate crafted ICMP version for packets. Crafted ICMP version for packets contains ICMP4 header, ICMP header with unreachable fragmentation needed on the DF set with small MT value and inner IP version header and inner UDP header. And specify source. This source is malicious ICMP sender, and target is target victim server, and remote is and try to control remote to target to remote PassMT value. Okay. And this page shows how to generate crafted ICMP version 6 packets. Crafted ICMP version 6 packet contains ICMP version 6 header, ICMP version, IP version 6 header, and crafted ICMP version 6 header that contains packet to big with small MT value. For example, 1280. And inner IP version 6 header and inner UDP header with large data size and field 0 to the end of packet. And this small code shows how to generate the packet. And this page shows verification of the result. On Linux 2.6.32, IP root get command shows that PassMT changes to 1280 on IP version 6, and PassMT changes to decrease to 552 on IP version 4. And this page shows verification result of FreeBSD and NetBSD. On FreeBSD, after attack, PassMTU cache changed and PassMTU decreased to 1272 and on NetBSD, after the attack, PassMTU changed to 1280. This table shows evaluation result of the attack. Domain variation plus plus for MTM resident PK paper shows that some implementations accept crafted ICMP version for fragmented need and DF set for UDP and PassMTU decreased to 552 or 296. And on Linux 2.6 case, Linux 2.6 accepts crafted ICMP version for fragmented need and DF set for UDP and PassMTU decreased to 552. And Linux 4.80 FreeBSD, NetBSD ignore crafted ICMP version for fragmented need and DF set for UDP. And FreeBSD, NetBSD case, they don't have code for crafted they don't have code for ICMP fragmentation needed and DF set for UDP. However, Linux and FreeBSD, NetBSD all accept crafted ICMP version 6 packet to big for UDP, and they and PassMTU decreased to 1280. This page shows summary of the attack. All the Linux systems accept crafted ICMP version of fragmented needle and DF set for UDP, and PassMT is changed to 552. And the BSC systems and newer Linux systems ignore ICMP version of fragmented needed and DF set for UDP. And BSD and Linux systems accept ICMP version of fragmented needed and DF set, ICMP version 6 packet to big for TCP, and change PassMT for matched TCP session. TCP case, they check existing TCP session table and not vulnerable. And many BSD and Linux systems accept crafted ICMP version 6 packet to big for UDP and PassMT decreased to 1280 and easy to set remotely. Then I'd like to propose that don't change PassMT discovery. ICMP version 6 packet to big for TCP and ICMP version for fragmented needed and DF set are necessary for TCP because TCP stack uses ICMP P2B fragments needed and DF set to adjust packet size, to adjust MSS. And UDP is safe to use with packet size up to 1280 on IP version 6. ICMP version 6 packet to big for UDP is vulnerable. And I'm proposing recommendations to avoid fragmentation in DNS. Sorry, this page is DNS. My draft proposes full service resolvers should set EDN0 requesters UDP payload size to 1220, and authoritative servers and full service resolvers should set EDN0 responders maximum payload size to 1220. And more, authoritative servers may send DNS responses with IP version 6 don't flag options. And full service resolvers may drop fragmented UDP responses derived from DNS before IP reassembly. It is a countermeasure against DNS cache poisoning attacks using IP fragmentation. And conclusion and questions. IP version 6 packet to big is important for TCP. And however, many OS accept crafted ICMP version 6 packet to big for UDP, and PassMT value is easy to decrease to 1280 remotely. How do you consider about PassMT discovery and fragmentation? Limit 1280 or disable? That's all.
Questions?
Yeah, Joel Yeagley. So this is definitely something I was thinking about in the context of could I get things to go lower than that, right? I don't see a real high value as a malicious agent in reducing someone's MTU from say 1500 to 1280, right? That's not, I mean, that's kind of me being an ass, I suppose, but like that's not nearly as costly as if you can say reduce it to 200, right? So I mean, this is essentially a product of us using an out of band signaling mechanism because the ICMP message is not embedded within the flow that it's purporting to control. That said, like I think the question here comes down to implementation advice. Like, if we still want path MTU discovery to work, then out-of-band messages are, of course, necessary. If you want to do it in-band, well, yeah, there's other mechanisms for doing that that are less susceptible to this kind of behavior. But unlike the case potentially in V4, particularly with really old like architectures where you really could reduce the MSS by a lot, I think this is less dangerous. I mean, if you're using a huge MTU, like say 65K, reducing it to 1280 is obviously quite detrimental to your performance and behavior. But, you know, those are not general internet cases.
Thank you. I prefer 1280 MTU is enough, I think.
Eric Klein, yeah, 1280 IPv6 decision to do 1280 seems like a better and better idea with every passing presentation today. This has been interesting. I think the original presentation as well about the fragmentation DNS attack that you mentioned in RIPE was also very detailed and fascinating. I think it's possible to do more sort of authentication, if you will, of the ICMP packet for TCP because you have some state tables. For UDP, you might not because it's not, the socket's not necessarily connected. But it does seem like if a socket is connected, the Linux kernel should bother to at least check the connected UDP sockets to verify that. Does it do that? Do you know?
Yes. If sender knows all sent UDP, all sent packet, then possible.
Yeah, if it's an unconnected socket, it might not maintain any state about that. But if it's connected, it would have it. So it should definitely at least try to scan that table. I think that would make sense. Yeah, this I thought was also a problem with eDNS0's MTU advertisement. There's no in-band fragmentation, which was like what 8085's predecessor recommended for how to write UDP applications. But I'm assuming the TC bit maybe solves all problems there. I'm not a DNS person.
Well, actually, I'm not really worried about TCP UDP fragmentation attacks in DNS because we do actually know how to deal with them. We can deal with them at the UDP at the DNS level if we have to. You just use TSIG. That generates a cryptographically secure signature over the UDP message, and there's no way a reassembled packet passes that. Now, as I suggested when this was originally brought up, that we use a well-known TSIG key to completely mitigate this problem. There isn't and looking at the way servers respond to unknown TSIGs, I don't believe there's a real problem other than deploying. That removes that complete thing. I'm not worried about DNS and fragmented UDP. We can solve that completely.
Thank you.
right, thank you very much. Mr. April.
Yes, I'm not as tall as Chris. I don't think anyone here is. So I'm Tim April. I'm from Akamai. I'm also working on this project with a few people that are not from Akamai. So we're proposing a new system that will help see changes that go into the DNS. So the overall goal of this project is to try and make it so that anyone who wants to see changes to the DNS in near real time or as close to real time as we possibly can get that data without having to go and pull the data yourself from the authorities. So the problem was back in late last year, early this year, there were a bunch of attacks on the DNS where attackers would get in, make changes very quickly, and then change them back, resulting in some queries, some changes going unnoticed by monitoring systems all around the world. And the nature of these short-term changes made it so that like mobile devices and things that were online but not actively doing any, or not actively having users interact with them, may have sent either credentials or all sorts of other stuff to those to the target machines where the data was changed. So the problem was, so the registration model that is used for the DNS, many of you probably already know, where the registrant talks to the registrar, to the registry, and then to the name servers. The problem here was the attackers that tried to get this data either modified records at the registrar without the registrant's knowledge, or in a couple cases had registrar credentials and modified them directly at the registry without the registrar knowing, resulting in takeovers that were essentially transparent to any of the people that cared about the names. And then many people that have high-value names will set up all of this monitoring stuff where you'll poll the registrar to make sure your names seem accurate. You may poll the registry. You may also poll the name servers directly and see what's coming back. But it really matters on what that polling window is, whether you're going to see these changes or not. The solution we're proposing here is to create a open system, kind of like RIS Live is for BGP updates, where the data owners push data into the system, and then it replicates the data back out to any of the end users that are interested. So that could be the domain owner, the domain users, anyone that relies on those objects, or people just monitoring for security reasons. So in phase one of what we're trying to do, we're going to try and get as much data from the registries as we can to push into this project. So this is essentially a pub subsystem that will send the data. The main goal is back to the registrant. So the people that own the domain should get updates about when anything changes in their name going forward. We're also talking about trying to get data from either GTLD name servers and then possibly the registrar, so that we can cross-check if the registrar sent us this update and then the registry sent us this update, that we know that they both know about this. What about the registrant? Did they send any data to us? If not, then we might notify them, or we might change how these notifications happen. It also lets the registrar subscribe to this. That's one arrow that I forgot to put on this graph, where the registrar could receive this data so that when the registry makes the change, they can notice that they actually got the update. And then, or if they didn't request the change and they see the update, they know something went horribly wrong. So we modeled this off of this, somewhat of the certificate transparency model. The one major change that we built into it was that we were going to try and build some monitoring and alerting on top of it, just as a way of, like, you'll still be able to get to the full log, but we wanted to make it so that you could also get real-time updates for whatever you're interested in, so you're not having to go and crawl the entire log all the time just to see the changes that you really want to see. So as I was saying, the data we want in is data from registries. Mostly the public zones that are out there, where think kind of like CZDS, the Centralized Domain Repositories Service from ICANN, but more up to date and faster. We have no interest in contact information. These slides are from the ICANN meeting, and I knew that was going to be a hot button topic if we were wanting who is information, because I don't want to deal with GDPR. And then we're hoping to output both a raw feed, so anyone who wants to go and look at the data can see it, and then the filtered updates for whatever you're interested in that could go over email, SMS, a webhook. I don't really care how you get it. If you're interested in this and want a different data format, let me know and we'll see what we can do. So the things we're working on now, we're trying to create an independent entity for it rather than putting it through some corporation or some for-profit company, so that it's a real open project rather than tied to some company. And then we're actually starting to build a POC with a few different data providers that we're hoping to get up before the end of the year, up and actually sending data to the end users. We're mostly presenting around a whole bunch of different places to see if people are interested in this. If you're a registry and we want to provide data, I'm happy to talk, or you can reach us at the contact information at the end of the slide. If you're a registrant and want to subscribe to this sort of thing, let us know and what your use case is so we can make sure that we try and cover that. If you're representing some sort of company and want to try and either help with resources or funding or something like that, we're happy to talk. Mostly we're deferring a bunch of that until we get the organizational bits stood up. Do you want to jump in now, Jared? Or?
Hi, Jared Mach. I'm just curious, this seems like it might be something that would fit in the DNS-ORG wheelhouse. I'm curious if there's a reason why not to park it there versus creating a new DNS monitoring organization.
We had some conversations about that. I'm trying to remember back to why it ended up that way. I'll have to.
I was just curious if there was an explicit or implicit thought process, and you can say, "I'll talk to you later offline." As well.
Yeah, like it's something that we will consider, that we had considered, and I'll see if we actually ruled it out or not. And then the other things that we're looking for is if you have experience with nonprofit stuff, that's something we're actively trying to work on. Sorry, go ahead.
Hello. Quick question. What's the license of the code developed?
We're trying to make it either MIT or GPL.
Thank you.
To respond to Job's reaction, that wasn't my, I don't care how it is, I just want it out there.
Hi, Giovanni Saidian. This is a nice project. I really like this idea. This is a problem we have. Of course, the problem here is not the technical part. It's to gain trust of the registries to share, and people to share data with you. You could also try maybe to build another system, like in parallel to that one, in which people can submit their own domains if they will, and then you start tracking them from the parent and the child delegation to see if they match. And whenever there's a change, you can just notify the same way.
So tracking that sort of change where we're getting data from below the second level is also something very much on our radar. And we had proposed going that method first, but we actually have more registry interest than we thought we were going to, where there are a handful of registries that are willing to hand us their full zone file in essentially the same format they send it to their TLD, their name servers. So we're going to try and push forward on that one because that requires less end user interaction now.
No, I mean, like, because I work for one TLD, CCTLD, and I'm pretty sure that we couldn't share. So
Yeah.
that's what I mean.
And it's like, we're hoping to get the TLDs we have online first and then go to the next level down and then try and target the other CCs after that.
That's a nice project. Thanks a lot for doing this.
Doug Montgomery, is there any notion of limiting the scope of what you can subscribe to monitor? In some sense, your resources, or can I subscribe to monitor any and all resources?
We were planning to try and make it so you can subscribe to whatever you'd like to. where the primary reason for that is if you look at, trying to remember if someone from VeriSign may be able to correct the domain name, but I think it's trans-trust.verisignlabs.com, where you can see all of the name servers that your delegations rely on. So like if you're in .org, you'll see that you have the .org name servers, you have all the affiliates name sets, and then you have the .net from VeriSign. .net and .com and VeriSign also rely on that. So you'd probably want to know any update. If you're really interested in name changes, you want to know all of the updates to any of those names and being able to subscribe to all of that. And then like if I'm a customer of, like if my mail is hosted on Google, I probably want to know if any of their names change so that I know if my mail is impacted. Things like that.
Randy Bush. The DNS is pretty big, so I think the subscribers are going to want to deal with scoping in many ways. But could you sometime somewhere post a URL for those of us who do run CCTLDs with a nice idiots page on how to push?
Yep. There's your URL. I didn't realize I only had one slide left. So I'll send it out to the IEPG list in a little bit with it's right now it's a very basic website. It just has the quick description of what we're doing. And then we have a form that you can go and say, I'm a registry and I'd like to send data. We don't have any of the infrastructure deployed yet. Once we do, I will come knocking. Will do. A question for you, actually, is what's the easiest way for you to send me data? I will note that and set up instructions. Thank you.
Lucy Lynch, responding to your question about setting up nonprofits. That's actually a relatively long and heavyweight process. Have you looked at the Linux Foundation sponsored projects?
We have not.
You might want to do that. They take a lot of the pain out of it, and they host things like Let's Encrypt, so you might be a good fit for them.
Okay. Keep that in mind. Thank you. Any other questions? I'm here all week if you want to catch me later.
All right, thanks. We're down to just the last official presenter. Oh, yeah, where are your slides? I know you did. I sure did. Wait a minute. So, yeah, we can do you instead of Randy, or we can do Randy and then you. Oh, Randy, you're up. I'll figure this out while we do that.
Is Lehman going to be speaking? So, hi, I'm Randy from IIJ Research and from Arcus Inc. How many people here remember in mid-April a DNS attack mess called Sea Turtle? Please, this is scary. This room's half DNS people. Come on. Okay, so what happened was DNS registration systems are a hierarchy, and a hierarchy is as strong as its weakest link. Bad actors were discovered by, I think it was Cisco Talos group, to be breaking links at the CCTLD and other TLD levels, and forging, and so on and so forth. No, this is not a talk about the DNS, but it's a talk about the weakness of hierarchy. And we have another hierarchy, which I did spend some time in. Luckily, Job, who invented it, is now promoting it much better than I could, and I'm relieved, but that's the RPKI. And it has the same weaknesses as the DNS in terms of a hierarchy. It has the same security model for the small deployment of DNS, which is object security as opposed to transport security. Okay, so if you can break things up chain, you've got it. And it has the way it is currently deployed, it has one wonderful, additional, brilliant weakness, which is all 5 of the registries at the root of the registry hierarchies are authoritative for the root. That is as if D.DE was also authoritative for dot. All 5 RIRs claim authority over 0/0. This is brilliant. Okay. In the security universe, the question isn't when this will be attacked. If this will be attacked, it is when this will be attacked. Okay. We're starting more and more. Thank you very much for the people who are deploying and for people like Job who are putting a lot of effort in getting deployment out there. We need to get the security of the system and the operational reliability cleaned up before the disasters happen, not after the first disaster happens. And it will happen. So some of the things we can do are pretty obvious. And getting the registries not to be authoritative for 0/0 is just one small step. Rudiger, you're ready to leap to the mic.
Why didn't we talk about this 2 years ago? Because then it wasn't this way.
Because I'm not usually used to you being snarky. Rudiger and I did talk about it 2 years ago, is his point, and we didn't succeed. I'm trying to explain that we tried to talk about it from an authority angle, and it was a bad model. It's a security problem. It's not just an authority problem. That's it.
Nobody except for Rudiger? Okay. Okay, Giovanni, I found your slides. I found them, but I have to actually open them. Randy's time's up.
Yeah. Right, so I'm standing here between you and lunch, but I think it's too early actually for that. So good morning, everybody. So this presentation is actually a work that I did together with some colleagues at ISI and also at the UPF. It's a topic that usually splits the crowd, the TTLs on DNS. So what happened, like we had a study last year on IMC, on TTLs and denial of service attacks, and we show how longer TTLs protect the users when there's denial of service attacks on authoritative servers. And I presented that to the ops folks at the CIDN, and they were like, all right, so it's nice to know that, so which TTLs should I use? I was like, oops, that's a different question. I haven't looked into that. So that's what it's trying to do here. This study has just been accepted last Thursday for publication at IMC this year in Amsterdam, which is perfect timing for this meeting. We have put online the submission version at this URL if you're interested. We're gonna, of course, create a revised version with the comments that we're gonna get last week. and that will follow will be online as well. Now, caching is the cornerstone of DNS performance. We know like a 15 millisecond query response time is real good, but 1 millisecond is far better coming from a cache hit. And as I said, we did this study last year. We'll look how caching protects users from authoritative service attacks on DDoS attacks on auth servers. And the thing with TTLs and DNS and caching is that the DNS TTL set at the zones, they can actually control caching duration at resolver side. So it actually affects latency and resilience indirectly, actually very directly. And there hasn't been a lot of evaluation on the topic. I'm just mentioned here to studies. There's some more on the paper we mentioned. And no research actually provides recommendations, or in the context of the IETF, I should use the word considerations. It's less controversial here, on which values are good for TTLs. Because it's a very challenge. It's a big challenge. It's a very challenging topic to determine what the good values are, because there are trade-offs, intrinsic trade-offs in the choices of TTLs. Short TTLs allows for operation ops teams to change quickly services, and long TTLs reduce latencies and service load. So given that and other sort of details, it's no surprise there's no consensus. So let's try to fill this gap with this study. And we break this down into 3 different research questions. The first one we asked, we need to know if resolvers in practice and in the wild, they're actually parent or child centric. I'm going to explain this in more details, but you can get the same information either from parent or child, depending on how your zone is configured, and they may have different TTL values. So you wanted to be sure who is actually in charge of the TTLs. And the second question we wanted to know is like how the different parts of the fully qualified domain name change effective TTL lifetime. For example, let's say you have your DNS provider use a certain DNS provider to gives you the NS records TTLs for a domain for 1 hour. What happens if your own A record is like 2 hours, and how those things interact with each other? And the third question that we addressed in this paper, we wanted to know, all right, we do some background work, some in 1 and 2 to see how the resolvers choose these TTLs and from where. But then we wanted to know how actually they are using OIL, how folks are deploying that. We know that the routes are very conservative, and they have to be for resilience, so they have longer TTLs, but CDNs, on the other hand, they usually have shorter TTLs because they want to change things very quickly. And our goal here is to provide recommendations or considerations on choosing those values. So let's start here with the first questions, resolver centricity. Like, if you, let's get here one TLD.cl from Chile. If you would ask for the NS record of .cl from one of the root servers, I just pick K root here, but it doesn't matter because it's all the same. If you ask for the NS record, you're going to get a response that says that with a TTL of this value here, which is like 2 days, and within that response, that value would come in this authority section part of the response. Now, you can also ask for the same question and type, instead of the root, you can ask for directly to the authoritative server itself, a.nic.cl, one of them. And then you're going to get the same answer, but with a different TTL here of 1 hour. And that's the child value. So you see there's a difference here for 2 days and 1 hour. And this one, the response actually of this one comes actually as an authoritative answer and comes within the answer field of the response. So it's quite confusing on DNS. Like a DNS response may have up to 3 parts: answer, authority, and additional. So that's why this one here comes in the answer, and it has even a flag. It just says that's actually the real authoritative. So we have like 2 different choices. There's an RFC who says that resolvers should trust this one, but we know how resolvers are in the wild. There's a lot of resolvers, different versions of code, and you cannot be really 100% sure if you're going to obey to that. So to investigate that, we chose .UI, which is from Uruguay. Why? Because, well, at the roots, as every single TLD, they had a TTL of 2 days, but in the time of this analysis, they had an NS record TTL at the child of 300 seconds and an A record for 120 seconds. So these values are very nice. Oh, sorry, for my experiments, they're very nice, but they're but not for operations. They change. I'm going to get to that later. They change those values. But if you're using RIPE Atlas, which I use all the time, and thanks guys from RIPE Atlas again for this platform, which is amazing. If you use it all the time, and we usually measure every 10 minutes. So if you run queries towards those records every 10 minutes you do it, you get a code cache because they're going to be expired by then. Now, so we did a bunch of measurements. I'm going to cover 2 of them here. The rest is in the paper. We queried for NS queries for NS records for that Uruguay, the A record with one of the authoritative name servers for Uruguay. And it just asked the probes, which were like roughly 15,000 of them, 16,000, to ask their local resolvers to get those records. We don't know, and we don't know where they're going to be coming from. And that's exactly what we want to know. So how do we know if the answers are actually, the resolvers are getting the answers from the parent or from the child? We just analyze the distribution of the TTLs that come back. So remember that at the parent, the root sets the TTL, the authoritative for any TLD to 2 days. But you see here the CDF, we see here that let's say 60%, or there's a huge spike here that most queries, for the A record, they come back with a TTL of 220 seconds, meaning that most resolvers are actually trusting the child value, not one set by the roots. And the same applies to the NS record. So what we see here is that most resolvers are child-centric, preferring the TTLs of the authoritative answers, and as should be. There's an RFC for that, 2181. I'm not sure if there's one of the authors here in the list. I think it's Randy is one of those, maybe, I don't know. In section 5.4.1, they specify this order that they should have, these records. So we did 2 other experiments. I'm not going to cover because it's kind of a repetition, but we need to double check that. And I said, well, let's use another domain name. Let's use google.com because those are TLDs, so maybe things will be different. But no, the results are the same, and we analyze passive data on DataNet as well. So most resolvers are child-centric. And I think that's a good thing because that gives the power to whoever actually owns the domains and not the parent. Now, second question. How different parts of the fully qualified domain name change TTL lifetime, how long it gets in caching. So let me explain. This is a little bit more tricky, but let me try to break this down. So we have this domain, cachetest.net, we use for testing, and I create a subzone called sub.cachetest.net, and I configure this domain in 2 different scenarios. The first one we use as the NS record for sub.cachetest.net, I use this name server. And the second scenario, out of bailiwick, we use this other one. In bailiwick, out of bailiwick, if you're not familiar, in bailiwick means that your name server is under the same zone, in this case, sub.cachetest.net, so it's part of this. And out of bailiwick, it means it's a different zone. And we intentionally set the TTL of the NS record to be shorter than the A, 1 hour versus 2 hours. And we wanted to know what happens with the answers in the caching once the NS record expires. Does the A is going to expire as well? So we wanted to know how these different components of DNS interact to give answers to the users. So that's pretty much how it looks like our setup at the .NET zone. That's what we have there. These are the details. And the cachetest.net, I also placed that on .NET. There's 1 0, 1 hour, and 1 hour. And in our zone that we actually take care of, we set the NS to 1 hour, the A record to 2 hours. And the trick is we start the measurements every 10 minutes with RIPE again, 15,000 vantage points. And at time equals to 9, we redirect, we just renumber our authoritative name server. And in this way, and we configured a new server to give a different answer. Why I'm doing this thing? Because I wanted to know later where the answer came from, if it's the new or the old, because that's the thing I wanted to evaluate, if they're respecting the TTL or not. And I actually asked my resolvers to ask quad A queries. They don't matter, but I'm not asking directly those records. I'm asking records that under that tree. And I use as vantage points the RIPE Atlas. So these are the 2 figures. The first one here is for the in bailiwick experiment. This one is for out of bailiwick. we see, let me start here. Every bar here, it shows a time being of 10 minutes. And what we do in both figures at the 10, the time equals to 0, from 0 to 10, we allow all the probes to ask for the squad A query, and all the answers come from the original server. That's the one that's configuring the zone. I think it's fine, both cases here. At time equals to 9, when you see this arrow here in both cases, we renumber the authoritative name server, and we see what happens. So for this time period here, this color here in both figures, we see the same behavior. What is that? People that knew they were having cached the values of these previous records, they still keep on going that because both of them are still valid, both A and NS. So nothing really new here. People that didn't know about that, they go to the new server because that's the one that's currently available. Now, that's when it gets interesting here. Here, only the TTL of the NS record expires because they had the TTL of 1 hour. So once it expires, the resolver has to refetch again that information. And we see here for the in-bailiwick experiment, most queries are coming actually from the new server, but a very different scenario here from the out-of-bailiwick. And most answers come actually from the old servers. So what is actually going on? In both cases, the A record still, in theory, is still valid in cache. So what is actually going on? And after that, some of them, after both expire in the second error here, some of them will keep on going to the original. This is a stick resolvers. These could also be sticky, but I have to drill down these ones because this is very surprising for me, by the way, but it's just, I don't think all of them are sticky. But the difference is like, and that's the important question thing here. Once your NS record expires and the resolver is going to get that, this is just an example of an in-bailiwick configuration. If your resolver is going to give this answer to you, but they're also going to include the glues here. If you don't, in this way, even though you had an NS record which has a duration of 2 hours, just by asking the NS in the in-bailiwick configuration, you're going to get also the glues. So the resolver is going to get that information, is going to update the cache, or try to figure out where this answer is located and update later. But if it's out of bailiwick, you don't get that. You just get the authoritative answer. So what matters in here is that like most recovers would trust cache day records on serving from different zones for out of bailiwick scenario. So the independence of the records actually depends on how your system is configured, your zone, if it's out of bailiwick or in bailiwick. And if it's in bailiwick, whenever the NS expires, it's going to force your A also to expire. Okay, so now let's move to the third research question: how people use TTLs in the wild. So we just like got a bunch of hit lists, the public popular lists. I know they're biased, but we're not interested. We're interested like in the big picture where they have, and we also use entire data nail zone, CCTLD, and all the TLDs available in the root zone. And you're gonna retrieve like TTLs for NS, A, Quad A, MX, and DNS kit. Sorry. And we focus only on child TTL values. Why? Because we found out that most resolvers are child-centric. And that's led to some discussions of our operators. So we see here on this first line on response, we see the number of domains that responded. And the first thing we found, the first lesson from this table you can see is that most of the domains, except for the root zone, they're only using out-of-bailiwick naming servers, the authoritative name servers. So if like you have like example.com, your name server would be example ns.example.net. So most of them, 9% and above, not on the roots. Not on the roots. The roots, a lot of them have mixed setup or in bailiwick only. It's like rough. Some of them are only in bailiwick. And I have here two figures of the CDF, the distributions of TTL records for different zones. So the way to read this is, for example, the root NS records here. From the child, you see like roughly less than 10% are within 24 hours. But if you look at the other zones, it's like 40% have a TTL that is like smaller than 1 day for the other zones here, for the NS record. And so that means that the root is more conservative. More people are having longer TTLs here, which is what we found. But if you look at the A records, you see the figures a little shifted to the left. I'm just going to move back and forth for you to see that. It's because the TTLs typically of the A records are shorter for the same domain than the NS records themselves. So that's what I'm trying to see here, how people actually deploy those values. And umbrella, it's a list, and I think it's the only one in our list that doesn't only have like second level domain information. They have like fully qualified and have a lot of CDN names that have like many parts of, and those look like CDN domains. They tend to be very short lived. Some of them use like only for one-time signaling. And that's why you see the umbrella list here having way short TTLs than the rest. Like 60% they have less than 10 minutes, which is like a lot. Now, so then we look at this, and I mean, if I have to choose, we first look in the TLDs. We found that 34 of them had a TTL for the NS record, which was under half an hour, and 122 under 2 hours on the child delegation. And we contacted 8 CCTLDs on this matter, and 6 responded. So 3 of them did not consider this question before. 2 said it was intentional. They were changing the infrastructure. They want to keep it low TTL values because if there were problems, it would be easy to reshuffle, reroute stuff. And 1 said it was the way they got it from the client because they are just an operator for this TLD, and they keep that way. And the cool thing about after the notification, we found that 3 TLDs actually increased the TTL of their NS and A records because they were not aware of that. And that was like, I didn't expect that to happen. But there were folks having a 30s. I mean, I'm going to get one case here of Uruguay. Sorry. It's something. Oh, yeah. It's not passing. Oh, Chris, can you help me out here?
Yes.
Next slide. No, back. Back. That's second.
Oh, you've broken it.
I'm not sure what.
This one?
I think next. No, here is fine. Or it should be fine now. Can move forward. Or next one.
Next one?
Yeah. Next one. 22. Yeah.
Whoa.
It's not working.
Certainly does not look happy.
Maybe you could open outside the browser.
Outside the browser? Who knows? I don't think this thing has anything but a browser on it, man.
Oh. All right. Oh, yeah. That one. Yes. 22. Probably because of the CDF and.
Oh.
So if we have a problem, you can also read from, I have it here. Let me just pull it from my email. So there's,
How about that?
yeah, perfect. Yeah. All right. No, that does the trick. So as I said, we know 3 CCTLDs, they actually changed their TTLs of their records. And one of them was Uruguay. We contacted them, and we actually asked permission to disclose that publicly. They were like, they had changed the value before in the past, and because they were doing some infrastructure changes, but then after that, they changed it again. And they went for the NS, they went for 300 seconds to 1 day. So I was lucky that I had measured them before they changed it. And one day I just double checked if they had changed it. They had changed it to 1 day. So I measured again. I asked 15,000 RIPE Atlas probes to send queries, and let's see the performance that they get. And this is the CDF you see here. And what we can see is that like the median response time for a client of RIPE before was 28 milliseconds for all the 15,000 vantage points for a TTL of 300 seconds. But after that, it went down to 8 milliseconds. And the 75th percentile went down from 183 to 21 milliseconds. You're shaving off like 160 milliseconds just by changing the TTL. I think that's a great change. Of course, it requires the records to be in cache. But that shows the power of TTLs here. You can actually improve a lot of response times. Next, let's see if it works. So, yeah. I think now it should be probably fine because there's no more figures. Anyways, let's see if it works. Oh, it doesn't. Yeah, well, that's fine. Yeah. So the question, so just going back to research questions, are resolvers parent or centric? So just answer them. Most are child centric. How the different parts interact. Bailiwick impacts a lot how caching works. Depends on your domain, how it's configured. How are TTLs used in the wild? The values are all over the place. Longer NSs than A and quad A's. In most of the domains we see, it's like they're out of bailiwick. Next, please. If it works. Oh, it's another CDF. Probably it's heavy to load. Definitely is a problem. Let me see if be in here. So slide 24. If it's not loading, we can go to 25. It's also fine. So I think the other one probably is not going to load because there are two figures. But anyway, we did an experiment to evaluate what is like the performance impact of using longer or shorter TTLs. It's going to be available later on the webpage of the IEPG, but slide 24, you're going to be able to see that longer TTLs improve the performance. And we found out that if you have two scenarios, if you have a domain name configured of a TTL of 60 seconds, 1 minute, and then if you have a domain name configured with a TTL of 1 day, another one with 60 seconds using Anycast is not going to help you as much as caching, because caching, even though caching helps a lot, caching helps much more than Anycast if the domain is cached. That's what I'm trying to say here. And we found out that if you use longer TTLs, we will be if you use longer TTLs, you observe like a reduced query loads in your server. We found a reduction of 77%, and let's hope it works this time. Slide 24 or 25, that we do it. Yeah.
It's not like whatever's on 24.
Yeah.
There's 24.
So that one. So you see here, that one, that's exactly what I said before. On this figure here on the left, you see the red color. We show the TTL of a domain for the bright probes towards one authoritative name server in unicast single location. And you see here the curve. And if you use a TTL, change the record and run in the same unicast for a server that actually has a TTL for just in a TTL to 1 day, you see the performance improves a lot. So here, you would see like 60% of the people, they're under 15 milliseconds if they use a TTL of 1 day, but if they use a TTL of 1 minute, they're roughly around 60 milliseconds. And Anycast, we run this on Anycast. We put the same zone, we put on Route 53 with a TTL of 1 minute. And my question was like, all right, let's see how much Anycast benefits the users in comparison to a longer TTL. Maybe I have a big Anycast network. I don't care about TTLs anymore. But for the point of view of performance, you see here that Anycast does improve that much for people which are very close. Improves longer here for people who are above 50. That's where you actually start to see the difference. But caching helps more if the domain is cached, of course, than Anycast. And that's a lesson here for operators. Next, if it works, please. Yeah, I generate those figures in PDF, and they tend to have a lot of data points. Sometimes they become heavy. Let's see. Oh yeah, I think it's not working. Yay. Yes. All right, so next one, please. So reasons for longer and shorter TTL. So longer TTL enables longer caching, which means faster responses, lower DNS traffic to your authoritative server, more robustness towards to deny service attacks. Shorter caching, on the other hand, supports operational changes. It's like faster for you to change stuff. can help in case you use like DNS-based response to DOS systems mitigation. It can cope better with DNS-based load balancing. So the takeaway here is like if organizations should like wait and this trade-offs here to find a good balance. Next. So recommendations or considerations. That we knew there's no single optimal TTL for all users, but for general users, longer TTLs, hours, or like even a day, if you will, are great. And like even like for TLDs as well. The exception is if you're running a DNS-based DOS protection service. So that we would like to have like a shorter TTL, so it allows you to quickly reconfigure your service. But if it was like only BGP-based, you don't care about that. A and Quad A records and NS relationship. For out-of-bailiwick, the records are cached independently, so we don't really care about the TTLs like. But if they're in bailiwick, we recommend to set the TTL of the A and Quad A should be shorter or equal to the NS. And location of those records as well. At least you should have one, preferably one at least, out of bailiwick name server in case the zone becomes unreachable. Next. Conclusions. So TTLs and DNS are a complex topic. We all know that. We'll carry out a bunch of like carefully designed experiments to figure out how those factors interact. We show that in the wild, there's a little consensus on how TTL values are used. And what I really liked about this paper, like the discussions of the ops teams for some CCTLDs actually led to improve users' experience. And in short, longer TTLs, if you can't do that, just do it. And this is also very good timing because we have a draft now on IETF, just this last line, Jared. And we're proposing considerations for DNS ops, and we're going to present that on Tuesday. And consideration number 5 about TTLs, it's all based on this paper now. Thanks. Any questions?
Hi, Jared. I was just curious if you were able to infer behavior from different software stacks of how the caching hierarchy interacted based upon whether or not you got the which answer you received.
So the way they did is measurements, like I used Ripe Atlas, and we kind of agnostic because I don't know which resolvers they are and what they do. I haven't looked into the problem, but I know someone who's looking into that. His name is Rafael. He works with Roland. I'm sure if Roland is here from University of Twente in Holland. He's actually looking into every single resolver version and to see what they're actually doing, because that's a different contribution, of course. I was looking into the big picture, but we need to know if the vendors are compliant to the RFC.
Yeah. I was I'm curious because I know many years ago people used the additional section for different attack, different attack vectors and stuff to go and poison, caches and stuff. And so the fact that you can tell which answer, because there's different answers in different places, you know which answer you received.
Yeah.
And whether or not you were able to infer from that what the resolver stack or stacks are doing from that. It seems like it'd be interesting additional.
That's a good point. I haven't looked at that. Yeah, I should look into that.
Okay.
I'm not sure if I don't think my data allows me to explain that, but I could carry other experiments to analyze that. Thanks.
Yep.
I think that's it then.
Anybody else? Good questions? Nope.
All
right. Thanks very much.
Thanks.
That was cool. Jeff.
Morning all. I'm Jeff Houston. I'm with APNIC. As Randy observed, IEPG meetings are exclusively for DNS and BGP and nothing else. And so Joel and the MTU work were merely aberrations. But, you hadn't had a BGP dose this morning, so you're early. You're not allowed out in the room until midday, so you've got to have your dose of BGP. This is actually a summary of an awful lot of data.
I was going to say 2018 was last year.
This is...
Oh, okay.
You'll actually see why it doesn't really matter. BGP is wonderful because of all these pieces of work. BGP is the one protocol that brings the entire internet back to you. Your details might vary with my details depending on where you sit in the routing mesh. But the whole issue about routing protocols is you get to see a complete topology of the entire internet. Not perfect, but not bad. And so in some ways, it gives you some amazing insights as to what the internet did. And if you take all of route views over all of its data, which starts around 93 in terms of hour by hour, and this is hour by hour, huge amount of data, you actually see the major events that happened in the internet. You know, the great internet boom and bust. God, I'll need a microscope. Just around here somewhere, you know, it happened. Big boom and bust. What actually really happened was the rise of consumer DSL. And that fueled through the early 2000s. And this whole thing about consumer-based internet drove inexorable growth. This is V4. But the remarkable thing is about all of this, that was when we started running out. That's the date at which IANA ran out, then APNIC, then RIPE, then LACNIC, and then we seem to be running on empty and running at an increased rate in terms of the routing size, even though we're not pushing more addresses into the routing system. So there's something going on there, and let's have a look at it. This is 24 months in detail of every peer of route views and every peer of RIPE's RIS. Bizarrely, route views sees more prefixes and oddly enough actually more addresses than RIS. They have much the same growth model, but in Europe there's certainly almost a /8 less of fine-grained detail in routing of address band than in route views. A number of possible reasons about this, including perhaps the notion of ghosts, prefixes that are sitting in the route table that were withdrawn at source but just continue to hum around in the routing system because the withdrawal is not universal. So yeah, an odd divergence. Average growth rate, much the same. And we can break it down in detail. And don't forget, there are no more new addresses. That's 2011 over there on the left, and that's when we ran out of really pushing large amounts of address space out into the internet. Yet we're growing at 52,000 prefixes per year in the V4 space, almost clockwork. And what is even odder in some ways is that the AS growth, 34,000 prefixes per year, is clockwork. So at some point, I don't know how you guys organize this as operators, you know, only 10 per day, and once there are 10, no more. No more, you got to line up tomorrow. Even on weekends, it's phenomenally uniform in terms of the growth rate of AS numbers. BGP for traffic engineering is still BGP for traffic engineering. Absolutely nothing has changed. Over that same extraordinary long period, the amount of more specifics, which used to be half of the routing table, is now 54% of the routing table, i.e. around half. So no matter what we say in the message about aggregate, 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 whoever's not listening is still not listening, and whoever is listening was always listening. And so the basic message has never really changed. The only thing that's really changed over those last few years is the average size of a routing advertisement. Because there are no new addresses, right? The address span that's being advertised for the last few years has been constant. So how do you get all those new routing advertisements in? You advertise smaller and smaller prefixes. The average routing size now spans 4,000/32s. It used to span around 7,000. So the average routing element is getting more and more finer as we progress. That's the address span, and you can see from around 2016 or so, that was the amount of address space that's being routed in the internet. We actually haven't unleashed the rest of the unadvertised addresses into the network. That's now relatively constant, sitting there at around 170/8s being advertised, and then just no more is coming out. Whoever's sitting on unadvertised addresses is sitting on them. Whoever was going to sell has possibly sold. I don't know, but we're not seeing more in the routing space. And the other thing that's pretty constant is the average AS path length. And that's going to be relatively important, but that's remained constant forever. Where I sit, it's a little under 6 ASs from where you sit. The actual value might be different, but its consistency might well be much the same unless you change your own routing. So this is another one. This is the amount of adjacencies. Now, the people on this list might vary depending on where you sit. Where I sit, I see Hurricane Electric with the greatest number of adjacencies, AS6939, but that's me. You look at yours, you might find a different one, but what you will find is around 9 to 10 ASs have an extraordinarily large number of adjacencies, number of neighbors, more than 1,000. About 2,000 or so have around, 10 or more adjacencies, and everyone else is out on the edge, 1 or 2 adjacencies. So that it almost looks like a power law distribution. It's not exactly obvious who sits in the top slot as a global constant, because I don't think it is. It depends on where you are, but that shape is the same no matter where you are. So the internet is very heavily not even a star network, it's a dense black hole kind of network where a very small number of folk do the bulk of the transit routing and everyone else just attaches at the end. And everyone wants to get as close as possible to those magic 10, right? There is no long AS path vectors flying around as sort of an industry norm. It's not. So this is why the actual date doesn't matter. Nothing's changed. The growth plots, it's just business as usual. The number of entries has reached, a magic 750,000, and it's keeping on growing at much the same rate. 52,000 entries a year, 34,000 ASs a year. And quite frankly, the way we're doing this, shorter and shorter prefixes, but exactly the same topology. So what about address exhaustion? Well, Aaron ran out, just really ran out. Afrinic's going to go in about May next year. LACNIC late this year. APNIC and Wright both have these last /8 policies, dribbling it out. APNIC late 2020, maybe if they change their policies, and I think they have to a /23 or something, it might last a bit longer, but effectively all that's left is sort of dribbling little bits and pieces. So what's driving growth right now in V4? Is it all transfers? Are these last /8s the factor, or is it leasing and address recovery? What if you take a snapshot of the routing system at the start of the year and a snapshot at the end of the year and eliminate everything that's in both tables? So the new stuff, you look at it and say, when was that allocated? So what appeared through the year, and when did the registries claim they give it out? In 2010, 80% of all the addresses we saw in the routing table at the end of the year were allocated within 12 months before when they first appeared. So in other words, you got an address, you routed it, and that was the major source of entries into the routing system. This is every year since then. And what you notice is it's a very sort of similar curve, but it keeps on dropping. So last year, only 20% of all the new addresses I saw in the routing system were actually allocated or assigned by an RIR in the last 12 months. Which kind of figures. What isn't quite so obvious is that almost half are really, really old. Really old, more than 20 years. So this is almost predates the RIR system. This is getting into legacy space. And what's happened in the intervening period is more and more of the legacy space relatively is bleeding back into the internet. And the amount of sort of transfer and trading actually hasn't changed a lot. This is the major factor of what's driving new addresses into the internet. I can look at that in a bit more detail by looking at the total amount of addresses that are marked as being out there, the amount that's advertised, and the amount that the RIRs are saying is out there, but I can't see them in the routing system. So that's that unadvertised address space blown up. And again, this gets interesting. Address exhaustion happened around here. We had 50/8s that weren't in the routing system. We now have 48. So this whole idea that transfers and trading would unleash a huge amount of address space that was otherwise dormant isn't supported by the facts. And in fact, the last 12 months were even more amazing, that the amount of unadvertised addresses actually rose, not fell. And there are a number of large transfer deals where the end result was the addresses that were previously advertised are now not advertised, which again is sort of anomalous behavior. So the drawdown from the RIR pool, just under a /8. The change in the unadvertised space, though, much, much higher. That's the text, yeah? You had a question.
Joel Yeagley, I can't speak to the details of any particular transfer, but I would observe that one of the things that people tend to require when they when they do transfer them is that the previous prefix announcements go away. So that actually means that some existing advertisements have gone away that I know of specifically prior to the address space being transferred.
This is kind of bears out with what we see too. And the predominant factor we see in the movement of addresses is towards various forms of CDNs and cloud providers. And they do go away. We're probably going to see them again at some point. But in this case, the go away was more than 3 months. So a relatively long quarantine period between previous use and next use. So we assigned some addresses from the RIR system, relatively small, but 2.1/8s actually were dropped into the quarantine pool. We'll probably see them again a little while later. And most of that was actually heading towards the cloud providers. Now, as far as I can see, the biggest buyers, not ISPs, cloud providers. ISPs don't seem to be doing much. V6, well, exponential growth. For all you V6 folk, you can smile. It's still exponential. It hasn't gone linear yet. This is probably, for them, really good news. Jared.
Yeah, actually, I had a question on the last slide.
Yeah. He's Jared Maunch. He's from...
Yeah, the speaker identified me. Thanks, Randy, though. So I'm still Jared, even just in case Randy forgot. I work for somebody. If he's interested in that, I'm curious if you've extrapolated out of the legacy space when you think that will exhaust, or do you have a slide on that?
I don't have a slide on it, but right now it's impossible to create a model that says it exhausts. If you look at that trend where there was a slight downward curve, but then it healed back up again, signal to noise kind of says we're going to sit between 45 and 50 for an awfully long time, and the stats aren't draining it. Now, I don't understand the market signals out there. You know, I was sitting there going, at $20 it's a steal, wait till it hits 1,000, and I'm still waiting, right? And maybe all these folk are waiting till it hits 1,000. I don't know. I don't know if it's a price-based thing, a logistic thing. They don't even know they own it. But, you know, there's no clear model of when that runs out.
I'm still Randy, but occasionally I try to have manners. Two things. One is I'm aware of ISPs purchasing address space from customers, legacy space from customers, and putting it in their back pocket for next year's customers in non-small amounts. I'm not talking /8s, but I'm talking 16s. The second thing is I just have a little trouble with your unrouted and legacy space doesn't exist. Some of your terminology there seemed a little extreme, but the motion, what's interesting is I think what we're seeing is a motion from stuff coming from the RIRs to stuff coming from existing holders. And if I were an RIR, I'd be very happy that I chose a rental model instead of a sale model.
I'll go back to this graph, which is, I think, what you're referring to. And this relatively large pool of addresses that appeared in the routing system that weren't there at the start of the year, whose original allocation age was a long time ago, and indeed in some cases predating the RIRs. And the observation is just that number is increasing. You know, the percent each year gets bigger. And we're mining ancient coal, right? This is not recent energy, it's a long time ago. We're good at this.
My name is Job Snijders. I was wondering if, when you present us a similar update in 2020 about the 2019 data, if you can also incorporate RPKI invalid announcements in a similar fashion as unadvertised drafts.
That's a good point. I at times have gone into looking at bogons, you know, and routing issues. It makes what I thought was a quick pack even longer, but it is useful to understand the extent to which we understand exactly what's in the routing system as being valid versus, wow, how did that get there? Yeah. Yes. Yeah,
I'm
good point.
specifically interested, we, through community effort, managed to reduce the number of invalids through social media, through peer
Sure.
pressure, by deploying. But there's this long tail of 2,000 prefixes that don't seem to move in any direction. Are those not in use? Are those up for sale? Like, who knows?
Good question. Yeah, okay.
I have two notes, not to the presenter, but to the chair, maybe. First of all, I cannot find the slides on the side.
That's my fault.
Okay. But the second one, I was surprised to see that the IEPG moved back to 2018.
It's hard to do a full analysis of 2019.
And it's hard for me to do even a partial analysis in under an hour. It takes me a lot longer to pull through this data. This is an extraordinary large amount of data. Yeah, and then I'll move on.
Hi, Doug, a quick question back to the age graph. When you see the spike of really old address spaces from your analysis, is this the original owners who are now putting this into play, or is it a sell-off of part of?
Oh, no,
like,
I assume, and you might say I'm out on a plank that's just broken behind me. I assume that the dates recorded in the RIR registry are real. And that's the date they left the shop. And when Aaron changed the date on a transfer, I write it back again because I want to know the date it first left the shop, not the date when they futzed around with it and changed something. So I'm going for the allocation date when a previously unallocated space becomes in play.
But in particular, if someone sold off part of a transferred part of a legacy allocation, you would hope that that transfer would be recorded, so that would look good.
Aaron recorded that with today's date, but I assign the date of the original allocation of the /8, whatever it was. So I record that as old space because it is old space. Yes. If SRI has the earlier one, that's the one I use. That's why a lot of this stuff is very old.
Hi, Delaney Elkins. You know, I'm curious as to the makeup of this unadvertised space. There's a lot of rumors that the US DOD is setting on a whole bunch of space, and it's a little, I said, there's a lot of rumors around about people have squatted on it. So I'm just curious, what are your thoughts and opinions on all of that?
The data is open. You can look too.
Jeff, have you done any analysis for these very old allocations to see what the relationship of the AS path is versus those old allocations when they have been announced?
No, I have not. So I haven't looked at AS path or changes in the advertisements. I haven't looked for where the AS and the addresses have been sold versus the addresses only. No, I haven't looked at that. It's an interesting place to look, but yeah.
Yeah, so the two things that I think might be interesting out of that. The first one is that if the AS paths have no relationship, that potentially implies that the allocation is just walking away, and that this is an allowed thing. But of course, the second thing I find interesting out of that, based on what some of our security friends tend to say, is that those spaces have been sort of prime pools where hijacks are happening. And this is where cross-correlation with the RPKI stuff becomes interesting.
That's a different talk. I do look at that. It's a different talk. I'll take it at that, and we'll press on. For all you V6 folk, you were waiting for this. This is where I'd got to. The exponential growth is still growing there. Interestingly, V6 risks and route views have a very consistent view. Now, this is a recent routing table. It's only a decade or so old in reality. There are fewer ghosts. And one of the issue is, to what extent is the V4 table full of prefixes that are actually unadvertised, but withdrawals haven't fully permeated through the entire system, and no one's going to permeate a second gratuitous withdrawal. And the fact that this is more concise and tighter, the risks and route views see exactly the same picture, is interesting. But more than that, I don't know. Ghost hunting is extremely difficult. The routing indicators, What was it? 52,000 a year in V4, 15,000 a year in V6, 3,400 ASNs in V4, 2,000 in V6. So that growth curve is slightly higher than linear. So V6 is certainly accelerating in growth faster than V4. More specifics, 1/3 of the routing table, predominantly 48s. If you were filtering on 32s or 35s, you wouldn't see an awful lot of V6. So more specifics at the 48 level, and also quite a lot of 64s where I sit. Your routers are going to melt one day. Take up a lot of the routing table. And the average routing size is now sitting at around a 32. So if you're filtering into 32, again, you're going to miss a lot out of here. So average size is getting smaller, much the same as V4. I've had to resort to a log scale because V6 is crazy. Advertised address span, it's linear in a log scale. Remember maths? If it's linear in a log scale, that means in a normal scale it would be exponential, but I couldn't get it on a graph. So that means it's growing, and it's growing at an exponential rate. Take my word for it. The interconnection in V6 is weird. And I suspect, because this is a relatively long baseline, it's the slow decline of the V6 tunnel overlay network and the increasing use of native connections actually means that this is behaving the way we would like it to behave. You're actually seeing something closer to the underlying topology. The fact that it's still noisy says there's still more work to do. And part of the reason I think why Hurricane is still up there is Hurricane did do a whole bunch of V6 tunnels. So again, your view will differ depending on where you are. The V4 shape, the V6 shape in connectivity, exactly the same. Small number of players right in the middle. In this case, only 2 AS numbers from where I sit have enormous numbers of adjacencies. You will probably see a different number from where you sit, and you might even see different players there. It's all relative. So overall, it's growing. What to expect? Well, some projections. This is V4 daily growth rates, 140 routes a day, 52,000 a year. You should prepare for within 2 years for up to, 1 million entries or so, despite address exhaustion, despite everything. There's no reason to suggest that that's going into a logistic curve. So if you're planning on fib size, and if you really want to stuff all your routes into a fib, if that's what you want to do, you're going to just have to grow at this kind of size. The only other way of doing it is don't put all your routes in the fib.
Yeah, a small comment on the predictions. As operators, we agreed that either people need to deploy RPKI origin validation, or we will deaggregate down to /24s to protect ourselves. So there may be some swinging later on, but let's hope that doesn't transpire.
This could get really fascinating because these are starting to get big numbers, even for big iron out there. The V6 daily growth rates, it's not linear, it's exponential. So those predictions get to be scary because they're 128 bits long. So at a linear, you kind of go yawn, but V6 is not growing in a linear rate, it's growing exponentially. We can expect within 5 years, 250,000 128-bit entries in the fib. So that starts to get significant. So in absolute terms, V6 table is rocketing along. It'll be about the same footprint in fib memory in about 5 years' time, the same footprint. Now, as long as you're prepared to do this, the internet will keep on running BGP. There's nothing intrinsically wrong with BGP scaling properties. It's going just fine. But if you don't want that size, you've got to think long and hard about how you want to route. The other part of this is the performance of BGP, which is the level of updates. This is where odd things happen in BGP that none of us can understand. This is the number of prefixes in V4. This is the number of updates in V4. This is the number of withdrawals in V4. The number of withdrawals per day is constant. Riddle me that one. With more people, more Brownian motion, more noise, more random actors, more this, more that, more withdrawals. No, withdrawals are a different thing. I don't understand. Roughly, what is that number? 10,000 a year, 10,000 per day, constantly. No matter where I look, I see a very similar number. But the one thing about this is that it does have a relationship to convergence performance. Randy.
Many of the announcements create implicit withdrawals, so the explicit withdrawals are not necessary.
Many of the announcements create implicit withdrawals. Yes. But why it's 10,000? Why doesn't it grow? Even the updates grow slowly. Whereas withdrawals, the number of explicit withdrawals kind of...
Because those updates have the implicit withdrawals.
Okay. Okay. Maybe. Maybe. It only ever takes an average of 2 updates for a prefix to converge to its new state. Whether it's withdrawal or a new path, on average, 2 updates. On average. And it's been the same since 2009 or even earlier. It converges at the same speed. And because of MRI intervals, that number actually translates to just around 50 seconds. So on average, around 50 seconds, whatever state it was going to now stays in that state for at least a minute, I think was the way I timed it. So it remains stable after that point. More than 2 MRI intervals. And that's been the same forever. This is viewed from 131072. I had a different graph that did all of route views all of the time, but it does take a lot of compute. It's the same property. It's exactly the same property because it's actually based on average AS path length. Because what you're looking at is there's a disturbance in the force, it has to propagate. A longer convergence time actually means a longer path to propagate through. Because you always like connecting into the core, updates happen really quickly. So into the core, back out again, you're done. So this is why it's relatively constant as far as I can see.
Jeff, so I think your observations are correct. I'd be a little cautious about tying it to MRAI type timers. Most people don't necessarily really have those for real, but queuing artifacts will look like that.
Well, if MRI has been as long, slow decline, whatever has replaced it has a very similar observed behavioral property.
I think what you're going to see, especially with your prior slide with the amount of BGP update noise, just simply the link that something is going to be in a queue tends to cause that to happen. So when you have a fair amount of stuff churning around, you get a lot of convergence niceties as a side effect of that. Where you actually get the pathological stuff is when you have short queues.
Okay. Either way, it's really good. That is an amazing thing. Grown by an order of 10, but convergence is much the same. So if you're worried about V4 update performance in BGP, don't bother. And whether it's MRI or whether it's queuing, as Jeff suggests, the underlying observation is the system is actually quite stable. From where I sit, V6 is entirely not that, and I'm always been wondering to what extent it's me and to what extent others see this. When I look further afield, I still see large amounts of operational instability in routing updates. Bizarre. The number of withdrawals is still low, but it's more variable. The number of updates is unbounded. It just seems that sometimes some routers just go into catatonic update announcement systems and sort of blah, 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 and never stop. Convergence performance as a result is all over the shop. There's no true average that maintains from day to day to the amount of updates that converge, and nor is there any real consistency in time. Now, whether this is the impact of tunnels close into the core or some other impact, there is something really different in BGP carrying V6 and BGP carrying V4. And the suspicion is it's something to do with topology, and the suspicion is, Jeff's shaking his head to say no, or something to do with overlays and tunnels and tunnel behavior. And if there's another explanation, someone should enlighten me, because I'm not enlightened.
Jeff has my joke, partial joke I made the Doug. There's too much quagga in the system. I wish I was joking.
Too much quagga in the system.
There's unfortunately some interesting artifacts, some of the older free routing software that was out and about, and it causes a huge amount of noise in the system. When I was doing work some number of years ago for the 4-byte AS transition stuff, we found that there was significant metastable routing updates going around, and it was showing up because it was incorrect 4-byte transition code, and a bit of chasing down since they ended up being a customer I had a little bit of visibility in at the time was a bunch of old Quagga boxes. So there's just literally, I think a lot of this noise is from the fact that a lot of V6 is being done, via software routing, and a lot of it's being done across tunnels, as you're saying, and a lot of the things that are plugging those things together at the moment, hopefully decreasing, is a bunch of older routing stacks that need work.
Well, the good news is, if you're right, it got better, but it's taken a long time to get there. Yeah.
Well, I think that partially that what you're seeing here is also your observation about these being over tunnels. As we get the more and more native V6 connectivity and the tunnels go away, people are shipping their routes across actual routers, which tend to actually be a little more stable versus over the things that are problematic.
Okay, thank you.
Randy Bush. Many years ago, some Australian nut said that V6 performance absolutely sucks due to tunnels and crazy peering agreements and so on and so forth. But that as more money started resting on V6, this will get fixed. For it to get fixed, those people playing in the game would benefit from even more analysis so we know what to fix. I think, finally people are coming to the conclusion that tunnels are as evil as gnats. But I think, as one of the other Jeffs is saying, that weak software is a problem.
It's worth investigating. This is not acceptable. As a production network, we shouldn't be here.
It's worth investigating.
And we should understand why this is still the case today. Yeah.
Yeah, Joel Yeagley. Yeah, I mean, that certainly is historically the case. Like, I can remember circa 1998, the reason our BGP implementation was shittier was literally because it was a different platform, because the SOUP 0 Cat 6500s that we had running the core did forward V6 at that point. And so, like, literally the Cisco 7000 that was sitting in the corner was doing the V6 overlay network. So it was literally shittier. I have observed in the process of building adjacencies in exchange points over a long period of time that people apply the principles of benign neglect to their deployment of V6 peering. If you take down a V4 peer, they notice pretty quickly, weirdly, because the traffic that they were saving a lot of money on stopped flowing. If you take down the V6 one, most of them don't notice for some time.
Dual stack, happy eyeballs,
yes.
cures every sin. Yeah.
Your V6 peering with Google tends to get a lot of notice because, like, the YouTubes flow over it. And so that property of benign neglect has been like slowly getting pushed out of that, but it's still readily apparent in a number of regions that I operate in, where that the management of those resources and the frequency with which they're up is demonstrably lower than the V4 ones, even in the case where they're running on the same hardware.
Well, I'm happy to look deeper, and others who are interested in this should look deeper as well. Certainly the data is available. Yeah.
Job again. The blue graph on the right side, it seems to stabilize the left graph, on the right side of the left graph. Yeah. Is that around February 2018?
Yes.
Because that's when a number of security updates were dispatched for Quagga-based BGP update.
You might well have observation of correlation and reason and causality. I don't know.
Janinkova. Again, I am curious if you could correlate those frequencies of updates and instability with actual traffic and actual users behind it.
We've had this conversation.
Yes, we're working on it.
And I assume that you were going to offer me some resources to help me do the analysis, and we're still in that conversation.
We are trying to, yeah. So, because I suspect it's still like the more users you have behind the prefix, the more stable it is. Because, yeah, it's happy eyeballs and people do not notice stuff if there are no complaints.
It's worth more investigation, Jen, no matter how we cut it. We need to understand this better. That's true. Do you need to run a successor protocol to BGP? I don't understand why you would need to in terms of, is BGP failing? No, it's not. Is it scaling? Well, it seems to be. There's no great sort of cracks appearing and no great huge holes in performance or even size. As long as you got the money, you can create the hardware, it will keep on working as a protocol. There might be other reasons to go to a different protocol, but BGP itself is still scaling. Fib size, line speeds, equipment costs, that's up to you guys. Nothing's going to get cheaper. The stuff is still going to grow, and as V6 grows, it's going to place more pressure on that. What you put in your cache, what you offload's up to you. But the routing space itself is going to keep on growing as far as I can see in both protocols. So, if you're running this stuff, understand what you're putting in your high-speed fib cards and manage that very carefully. You can't ignore it. It's going to get more and more critical. And another thing that gets ignored is V4, V6 partitioning in your fib. That allocation, which was normally static in a lot of router configs, 10% V6, 90% V4, will not work even today. You need to look at that balance carefully. And quite frankly, you don't need to carry every route all the time. You can just default this stuff outwards. End of rant. Randy.
Randy again. One place I'd quibble is the cost of the hardware. It falls radically, and it's held up artificially by market forces, et cetera, but in really my entire, I've been in this field for 50-something years, those damn hardware people are just killer. They drive the cost down and down and the scaling up and up and up. Bet on them. Don't bet on the software.
Fair enough.
So you can bet on the software bugs. Good margin in that. So I'm not that worried about router scaling. I'm worried about the market forces driving what I have to pay to purchase it. But maybe some things will happen.
Any other comments or questions? That's me. Thanks a lot.
Thank you. I think we're essentially out of time. See you in 3 months. What? And we're done.
No,